In topic 4.1 special relativity, we're going to look into the theory that Albert Einstein introduced in 1905 and a number of the phenomena that go along with that. It may seem a lot like science fiction, some of the concepts we're going to cover, but there's a lot of evidence that we can point to that actually supports these phenomena, and so it's one of those situations where you need to be comfortable with the fact that the way that you need to approach this topic is not the same as the way that you will have approached previous topics. You may find that you get confused with a lot of the concepts that we cover, but bear with it, ask questions where you need to, and hopefully we'll be able to get you to a stage where you can make sense of these concepts. Now, before we launch into the concepts related to the theory of special relativity, as you can see by the highlighted dot point here, we're going to have a look at why it is that we actually need to even consider special relativity. And that comes back to the fact that our understanding of physics is only part of the picture. And I'll explain that by talking about Newtonian physics, and then we'll start to bring in some of these ideas of relativity. Now, the idea of Newtonian physics is that it describes everything that we see around us. It's sometimes referred to as classical mechanics as well, so all of those concepts that we've covered up to this point in time, and does a really good job of explaining all of the phenomena that we can see around us, all of the interactions of mass and matter, and the forces that act on them. And so we can go back here to consider Newton's first, second and third laws. We can also think about the Suvat equations, so how they can be used to describe how matter moves, the accelerations and the speeds that are involved, and they provide a good approximation for everything that we see around us. And so that means whenever we see objects moving, whenever we see them interacting, colliding, exerting forces on each other, they can replicate those scenarios. So if we apply those equations, we can predict where objects will be located, or where they'll be moving, or how fast they'll be moving, using Newtonian physics. But while it provides a good approximation for our physical world, it's not a full and complete picture of how the universe actually operates. And a good example of this was an experiment that was conducted in 1941 by Rossi and Hall, where they made some measurements of muon decay. Now, muons are covered in more detail in subtopic 4.3, but we'll just talk about the observations that they made here. And more importantly, to start with, is that those observations that they made couldn't be explained using Newtonian physics. So if you tried to apply those laws of motion as developed from Newton's laws of motion regarding forces, the explanation of the observations from this experiment couldn't be explained using those laws of physics. Now, as I said, for more information about muons, you'll need to go to subtopic 4.3, but just to give you a brief background here, muon is a negatively charged particle, so it has the same charge on it that an electron does, and it's an elementary particle, so it's one of the building blocks of the universe, and while it has the same charge as an electron, it's a much more massive particle, and that means that it has a much greater mass when we say that it's more massive, and that mass is about 207 times greater than an electron. And that large mass means that it's fairly unstable. So half-life, if you recall back to content that we covered in year 11, is the amount of time it takes for half of the muons that you have present to decay into other subatomic particles. And so the half-life of muons is a fairly short 1.56 microseconds. The muons that Rossi and Hall observed were actually produced in the upper atmosphere. So while they can be produced in a number of different ways, so they could be produced in atom smashes like the Large Hadron Collider, the ones that we're considering here were produced in the upper atmosphere, and they are a byproduct of cosmic rays when they bombard particles in the upper atmosphere. So those cosmic rays usually colliding with molecules up in the upper atmosphere, would then produce pions as a product, and also kaons and a number of other things. Those pions and kaons would then decay into muons, but it's really the muons that we're most interested in. And when they're produced, those muons would be moving at speeds close to the speed of light. And so by close to the speed of light, we're talking sort of 99% or higher. And that speed is when they fall towards the Earth. So there's the setup of this particular experiment. The way that these muons were then measured is the important thing that we need to consider. In their experiment, Rossi and Hall measured the number of muons that were passing a detector at a height of 2,000 or about 2,000 meters. It was a little bit less than that. They actually conducted it on the top of a mountain, and by counting the number of muons per hour, they weren't really looking at how long the muons were existing. It's more just sort of detecting how many muons were present at that altitude. And the measurement that they recorded there was the initial measurement's not particularly important. We'll only mention it here so that we've got a point of reference. And as I said, at that altitude of about 2,000 meters was about 560 per hour. So each hour they were detecting about 560 muons that were moving past the detector. And in this experiment, they also took the corresponding measurement at sea level. And by making a comparison between the two is where the discrepancy starts to become apparent. And we'll talk about that in a bit more detail. So if we look at Newtonian physics, considering the speed with which the muons are moving, and also the fact that they have a very short half-life, what we would expect is that as they're continuing to fall at 2,000 meters, the muons will decay, so we'll end up with less of them when making the measurement at sea level. But when they're moving at near the speed of light, even moving at that fast speed, to cover that distance, it should take them 6.5 microseconds. So you can see there that 6.5 microseconds is a fair bit longer than their half-life. It's just over 4 half-lives. And if it's just over 4 half-lives, that means that we would expect that the count of the muons would be around about 30 per hour. So given that it's just over 4, half to the power of 4 would be 35 if we take 560 multiplied by half to the power of 4. And so it should have been around about 30 per hour as the measurement at sea level. The actual measurement was 422. So you can see that measurement is significantly larger than what would be predicted by Newtonian physics, and so Newtonian physics clearly isn't explaining this scenario well enough, and there has to be some other explanation to get that measurement. Now if it was significantly lower than 30 per hour, then perhaps there are other factors that are at play, but this measurement of 422 per hour being much larger means that we need to consider another type of physics that's involved. And that physics is special relativity. When the theory of special relativity was applied, the measurements that they recorded matched with the predictions of special relativity. Now there are a couple of ways to consider this scenario, and won't go into any detail here because we'll cover it later in some of the particular phenomena that we're dealing with. But the two things to be aware of is one, that the measurements from Earth record the half-life as being longer So it looks like the time of the muons is actually sort of stretched out, and that's a phenomenon known as time dilation. The other alternative is to consider it from the perspective of the muon itself, and the way to consider that is that the distance that the muon would measure it has fallen is not actually 2,000 meters, but significantly shorter at around about 180 meters. And that phenomenon is known as length contraction. But as I said, we'll talk about those two phenomena in much more detail in later videos. But just be aware that that's the explanation that will help to put this particular experiment into context. Moving forwards, we'll have a look at the postulates of relativity and some of the significant underlying aspects, and then get on to those phenomena that I've just mentioned.